Hi everyone, uh, welcome to the first session. Okay, welcome to the first session of week 3, day 2. Today we're going to be looking at stats and distributions. Gonna know about some more. Like we're going to take a look at three of them, which we're going to be working mostly for now. And plus for the hypothesis testing, we're going to be also taking a look at three of them. And finally, we will see how to create actionable insights because uh, doing all of these insights, sorry guys, this is better. So yeah, so as I was saying, so like even after creating a lot of insights or a lot of analysis would not ensure us that we're going to be that's going to be helpful in any way. So creating this creating actionable insights, it's very crucial for like data analysis, machine learning, and anything that's related to data. When you're working with it, you're going to be required to give actionable insights or to give recommendations and so on. So that's going to be uh, that should be in your report. So that's what we're going to be taking a look at. So as usual, if you have any question, if anything is not clear or if my idea is not clear or so on, please let me know. Okay. Okay. So let's start with like why it matters. So why starting from raw data uh, to answering real questions why it matters. So before we build like complex predictive models and doing the analysis, we must first understand our data and validate our assumption. So almost always, we start with an assumption. So we will also see that with the hypothesis testing. So we have these assumptions that we have. It could be so these assumptions could arise from our knowledge about the data or from our experience in the industry. So, like when you start, like if you have worked in an industry for so long, you might find like some patterns. You might not notice some patterns, and whenever you start this analysis or anything with that, you will start with assumptions, right? So that's one thing. So you must first understand the data in order to validate your assumptions and so on. So in any field, this can be in any field, not just data analysis and data engineering and like anything related to data. Moving from I think to I know is a very key to success because before analyzing the data, you may think the solution or the like the cause or so or anything like related to that. So that's I think, and coming from that to I know, like being sure of it, is a very driving force to success. Because of course there is also risk because a lot of decisions could be done based on your analysis and results. That's your I know. So data-driven decision making is a process of using facts, matrices, and data to guide strategic business decisions that align with your goals. So keep that in mind. So why it matters? So it reduces biases because, like I said earlier, like based on like or depending on your experience, or depending of what you know or what you heard, you may have some, like expectations or assumptions. So it's like by having data-driven decision making, you will reduce this bias. So it grounds your decision in objective reality, not by just intuition, like not by I think, or like uh, you will have this evidence to rely. And it increases consistency because it creates a framework for making reliable choice time and time again. It uncovers opportunities. It helps you spot trends, insufficiencies, in close areas that would otherwise be unnoticed. So, as you can see, it's very necessary, right? We cannot overlook this. So let's start with like the statistics description, which we can like start from understanding the shape of the data. So only by looking at the shape of the data, how it's distributed, and so on, we can actually make some assumptions and like have some understanding about the data. So this statistical distributions is a function that shows you the possible values for a variance and uh, how often like they may occur. Right? So think of it as a blueprint for your data, describing its underlying pattern and probability. And so like it allows you to model real world data and process and understand its value. So it's very crucial. When you start with any data, it's very necessary to start with understanding the shape of the data. Like you do like in ADA and so on and so on. So it's really necessary. So this will like knowing the distributions and understanding the shape of the data will help you with identifying unexpected outcomes and outliers. If there are any outliers, you will immediately know them. You make more accurate forecasts and have a better hypothesis, you may say also, and choose the right statistical test for your analysis. So this is very crucial because um, like it's going to be slippery slope. If you miss this, you're gonna miss a lot of things because it depends on your knowledge of the data. Because the tests you may assume you may start with the like the analysis you may do and so on and so on does depend on the type of the data you have, the distribution of the data, and like the like the shape of the data, you may say. So failing to understand this or like failing to understand it in the right way will cost you a lot of time and effort. So make sure you like start with the basics. Okay? Yeah. Okay. So let's start with some of the most. So I think I should remove this one. Yeah. So let's start with the most. I just keep that one because it's a repetition. Okay. Uh, so let's start with the most common ones, which is the bear curve. We're gonna see also the skewed ones. And yes, is that a question? Um, okay, I think yeah. So the data distribution. So let's start with the normal distribution, which is the bell curve. So you may see this in a lot of places. It's just a symmetric bell-shaped curve where the mean, the mode, and the median are the same. So here you can see an example here. Actually, the mean, the mode, and the median are the same or equal, and it's symmetrical on both sides. And this is the asymptotic tail. Like it doesn't cross each other, but it just approaches that. It just approaches it. Sorry. So the shape is symmetric and it's bell curved, where the mean, the median, and the mode are the same. So it tells us that the most values clustered around the average or like in the middle, right? So the values that are far from the average are increasingly rare, and the data is predictable and balanced. So there are a lot of examples for this one. So I believe like most of us have seen like this kind of shaped graph. So this means, for example, the distribution of customer satisfaction on a scale from 1 to 10. Like I think uh, height could be like the best example here. So if you compare heights in your class, you may end up with a similar graph because a lot of you are on the same height, but there will be some like one or two people that are very tall and a couple of people that are very short. So like it's very rare as you go far from the middle, but at the middle is going to be mean. So a lot of us are on the same height, but like there are some cases that we'll find a very long or a very short. So that's height, blood pressure of a large population. I think it's the best example. And why it doesn't matter? So it's a foundation for a lot of statistical tests, especially like the t-test, which we will see, of course. And many methods assume that the data or the error, at least, like because the measurement errors of a calibrated machine can be also attributed to that one as well, are normal. So a lot of places actually assume that their data is normal. So it's very important to understand its properties. So skewed distributions, it could be from like skewed to the right or skewed to the left. For this example, it's skewed to the right. Oh, sorry, it's skewed to the left actually. It's a negative one. Sorry, I think I will adjust the image here, but it's a symmetric curve, so it's not symmetric as the one before, but it's a symmetric curve. And the example is a right skewed, so I will change the image. Don't worry about it. But where most of the values are clustered on the left, with a long tail of a very few high values to the right. So here it's actually going to be, yeah, but you will get, I think, the idea of how it changes. Sorry about that. And it tells us that most events are low valued, but there are small chance that the very high value events, like for the example. So yeah, in this case, the mean is pulled higher and the median is than the median. And the insurance claim amount, you will see, for example, insurance claim amount, most claims are small, but few are catastrophically high. So like you can see that if you work in insurance, like a lot of claims could be very low or small, but there will be some like when a factory burns down, like stuff like that, it's very large. So and the customer income and purchase value, most customer have a modest income purchase, but very few have very high time spent on the website. Most people may leave quickly, but some stay far longer. So why is it important? The mean can be misleading metric for skewed data. So the median is more often better measured than the typical value. In the skew can lead to several understatement of things. So like like I said, like if you ignore the distribution of the data or like the shape of the data, it uh, lead to severe underestimation of the risk. So, yeah. Okay. So the last one under the distributions, we will see the position like distribution, sorry, and the modeling event count. So it's just an example. So the bar chart of non-negative whole number. So like you have to make sure that it's a whole number and it's not a negative. So just a count, we can see it as a count. So it tells you that the probability of a given number of events happening in a fixed interval of time or space, given that the average rate of occurrence, which is lambda. So, for example, claim frequency, how many people or the number of claims filed by policyholders in a year. So, operation, the number of customer support calls received in an hour. And from the marketing team, you can see the number of clicks on an ad per day. So it's just a classic tool of just you can see it as a frequency model for frequency of event, how many times it happened. It's essential for resource planning. Like if the operation teams have claimed that the number of customer calls received an hour is very high, you can staff the the call center, and for frequency severity approach to this model. So here you can see just one example of this one. Uh, yeah, so that's just the summary of the uh, statistics. And for answering and for asking and answering questions with data. So let's start with the hypothesis testing. So hypothesis testing is a formal procedure for checking if your data supports a particular theory. It helps you distinguishing a local predict from random chances. So the core concept are two, which is the null hypothesis and the alternative hypothesis. So the null hypothesis, as the name indicates, the default or no effect assumption. So it just assumes that there is no effect, or it's just the default. So for instance, there is no difference between the average purchase value between group A and group B. So this is called the null hypothesis. And the alternative hypothesis is just the one that you want to prove. So for example, there is a significant difference between the average purchase value between the group A and the group B. So this is the hypothesis. So you have the null hypothesis and the one you want to prove, which is the alternative hypothesis. And the p-value is just the probability. I think you have seen this earlier. They're just the probability of observing the data if the null hypothesis were true. So typically we take this 5%. So if it is above 5%, which we just um, like reject the null value, and if it is greater, we just accept it. Like a low p-value, typically less than a p, like 5% or 0.05, gives you a reason to reject. Sorry, to reject the hypothesis. I said it other way. So we will see examples. So don't worry about this one if it is new to you. But let's just take a look at the three tests that we have here. So the first one is the t-test. It's just the purpose is to just compare average or the mean value of any numerical variables between two different groups. So, for example, if you have a question, if you are wondering, does our marketing campaign of Group B generate higher average revenue per user than old campaign just group? So the null hypothesis could be that it's not going to be different, right? So the average revenue is the same for both campaigns. So mu1 and mu2 are equal, mu A and mu B, which is group A and group B, are equal. We assume that. In the null hypothesis and for the alternative hypothesis, which you want to prove, you will say that the average revenue is different for the two campaigns. So you have two campaigns, which is group A and group B. So you want to prove or to show that there is a difference between their generated revenue. So the null hypothesis is going to say they are equal. No, there is no difference, and the alternative is going to be it's not the same. So when to use it? When you have one numerical variable, the total claim for your example, and one categorical variable, exactly two labels. For example, if you want to check the total claims between the gender. So if you are wondering, there is a significant difference between the claims taken by male and female. So then a hypothesis it's not different. It's the same for both genders, and then a hypothesis it's different. So we will see examples. So don't worry about it. So the purpose for ANOVA is just an extension of t-test. It just compares the average of the numerical variables across groups. But the difference here, so the earlier one was between two groups, for example, gender and so on. But here it's for three or more groups. So it's just an extension of the earlier one. Okay. So for example, if you are wondering if there is a difference, like does the different vehicle types, for example, sedan, they have SUV and truck, do they have different average claim amount? So the null hypothesis would be the average claim amount is the same for all vehicle types, so it doesn't depend on the vehicle type. And alternative one is going to be at least one vehicle type has a different average claim amount. So when to use it? So whenever, like, just the simple and straightforward answer, whenever there is more than two categorical variables and one numerical variables. So if you have one numerical variables and two categorical variables, you will just go with the t-test. And if it is more than two variables, categorical variables, you will just go with the ANOVA. And the last one here is going to be the chi-test, which is just the relationship between two categorical variables and compare the observed frequencies of expected frequencies. So, for example, if you are wondering, is there a relationship between customers' gender and the type of vehicle they insure? So, if you have just sedan and SUV and male and female, we may just use this one. So gender and independence, there is no association is going to be your null hypothesis. And gender and types are independent. Dependent is going to be like alternative hypothesis. So when to use it, when you have two categorical variables, for example, gender and numerical type, you may use this one without or with the absence of numerical variables. Yeah. Okay. So before we move on to the statistical significance and actionable insights, is there any questions? Is everything clear, guys? So I want to guess that.
One quick question. I'm wondering if the P is below 0.05, does that necessarily mean we have above 95% confidence, or is that a different metric? I forget.
No, it's a different metric.
Same metric, right? P below 0.05 means you have a 95% confidence.
No.
It's a different one.
Yes.
Okay, thank you.
Yeah, we will just see it. Okay? Like p-value. We will see it, but yeah, it's a different one.
Okay, thank you.
What's decided? It's low, but okay, it's on my side. Okay, so yeah, okay. Okay, I think it's just it's just conversation. So is it clear, guys? Before I move on, is it clear? Thank you, Nabil, for the question. Is it clear for the rest of us? Okay, good.
You cut out a little bit. I'm not sure if it's my connection or if it was your connection.
So it's not like, are you talking about my audio, Nabil?
Yeah, so I can hear you, but you kind of cut in and out.
Oh, now or be like during the session while I was?
It was when you're answering the question. It was okay. It was kind of okay during the session. You cut out for a little bit after you're answering my question, and then it's coming back now. Okay, it's not as clear as it normally is.
Okay, let me try this one. Okay, what I was.
Now it's all right. It's not the best, but it's doable. Oh, sorry, it might be my problem today. I'll try a different connection on my end.
Okay. Yeah. Okay. Good. Okay. If everything is clear, I think we can move on to the next slides, to the next part, which is just getting actionable results. Because like you have done all these tests, all these analysis, all these you have built a model and so on, but you need to communicate these things to your audience, of course. So let's go from like what we have seen from the p-test, like the tests, to getting actionable insights. So from statistical significance to actionable insights is going to help us with that one. So finding low p-value. So you have to understand this. I think let's go with this one. So having a low p-value doesn't mean that it's so the p-value tells us if you have if an effect is likely to be real or just a random noise. So let me just explain more on this one. Okay, so the p-value is just there to help us. So when you do the analysis, you may get like, for instance, for the gender and the total claim value example. So you may find that the male gender is taking a lot of total claims. So that's done by the t-value, right? So when you are performing the t-test, you have seen that the male gender is taking a lot of total claims. So you have seen that there is a difference, right? But in order to just accept and like reject the null hypothesis, you will take a look at the p-value. So this will help us identify if this what have occurred or your analysis is real or just random noise. So sometimes you may get random noises, or just you may get analysis, but it might not be repeated, right? So even if you have a higher value for the male, it may be caused by outliers. So do you get me? So so the p-value is there for to help us identify if it's just a random value or a random noise, or is this really happening. So are the male are the males taking a lot of total claims, or is just a random noise, or caused by some like outliers and so on and so on. So having understanding what the p-value does and using it correctly is very crucial, because just depending, or just being dependent on the tests, and to just reject an hypothesis or accept it is not ideal or a good thing to do. So I just wanted to highlight that. So it doesn't tell you that it doesn't tell you how big the effect is, or what to do about it. So the real value is created in the steps that you follow after you have got the test, the p-value tests result, and the result from the tests. So having this understanding after you have done the test and so on and so on, having answered these questions is going to help us with identifying or creating the real value. Okay, so we can use a simple but powerful framework in order to help us drive these insights. Okay, so the first one is what. So state the statistical finding clearly and concisely. So what have you found when you were performing the statistics, like the tests, right? So you have done the tests, you have done things. So the first thing you need to do is to just communicate what you have done. So state the statistical finding clearly and concisely. That's the first step. And the second one is answering so what. So you have found that the male the value shows that the male gender is having or taking a lot of total claims. So what? So interpreting the finding comes next, right? So what does this mean in the business context, or how big is the effect? I think there is a car passing by, so if the noise is not clear, just says okay, I will repeat it. But so what is going to help you interpret the finding in the business context? So yeah, for this week, you're dealing with, or you're working with the insurance data, right? So you will have some findings. So you have some, so you have answered what? So you have answered, or you have communicated your findings. So what comes next is interpreting it in the business context. So you have to highlight this one. The business context is the keyword here. So you will interpret your finding with the business context. And then, of course, the last part, which is equally important, is now what? So you have found a result, you have interpreted the result, and then what? So you have to come up with a recommendation. So that's what we mean by having these three components is what we mean by data-driven decision making. So you have the data, you have the analysis, and you have the interpretation, and then you have the recommendation that's going to help with the decision making. So now what is going to help you communicate recommendation, providing a recommendation that is data-driven. So you will recommend a specific data-driven action, or a next step that you would like to do, or you would like to see. So having this understanding is going to help you a lot when you work with data. So let's see, with this framework, let's see two examples, with one with ANOVA test and the next one with the chart test, and we will suggest some common pitfalls to avoid and some good things to do or to follow. So let's start with the example one, which is insight from ANOVA test. So let me just catch you up with the scenario. So for this example, so assume that you are working with an insurance data. That actually is what you are doing right now. And so you have used the ANOVA test in order to see if the average claim amount differs across three provenances. So you have three provenances, and you have the total claim, which is the numerical value or the numerical column, and you have the three provenances which are categorical, right? So assume that you have done the test and you have seen the result. So you have seen that the ANOVA, just to refresh your mind, so the hypothesis, the null hypothesis is going to be that there is no difference between the average claim between these three preferences, and the alternative is going to be that there is a significant, or there is a difference in average claim among provenances, the three provenances. So the result after you have done this, the result is that the ANOVA test is statistically significant, which is 0.01. So this means rejecting the hypothesis that the average claim are equal or equal across the provenance, or you may say that there is no difference. So you have 0.01 p-value, which is less than 0.01. So you have rejected the null hypothesis that the average claim are equal. So what? Okay, so you have this data. So what? So the post hoc analysis showed that the average claim in provenance B. So this is just assumption. So just an example. That the claim in B, which is 22%, is higher than the provenances A and C. That means our financial risk exposure is not uniform between the provenances. So we are currently more valuable to a large loss in provenance B, because the average is not the same to all provenances, which will negatively impact our profitability in that region, in the provenance B. So this is your interpretation of the result. So now what? So what is your recommendation based on your analysis? So you would recommend that the company initiates a targeted investigation into the underlying risk factors, specifically to the provenance in question, which is provenance B. It might be higher vehicle theft rate, road conditions, that the claim is higher. You want to you are just recommending that the company initiates an investigation into what's causing this higher average claims in this region. So is it higher theft rates, vehicle theft rates, or is it the road condition? Is it a bad condition? Or based on the finding, then you should model a potential premium adjustment for this specific region. So you may make the payment higher and so on. So is that clear, guys? Is it clear? Is it making sense? So is the example clear? It's clear, right? The example. Okay. So let's see another example, which is by using chi test, which is comparison between two categorical values. So for this scenario, again, let me just catch you up to speed. So you have chose a chi-squared test to see if there is a relationship between having anti-theft device and having a claim have a relationship. So the null test here would be that there is no relationship between having an anti-theft device and having a claim, and the alternative is going to be that there is a difference. So these are true or false. Okay, anti-theft, is there an anti-theft on this car? It's going to be true or false, and having a claim is going to be true or false. So they are both categorical. So what have you found? So by using the chi test, you have statistically found that it's 0.05, so indicating a strong association between having anti-theft and claim status. So the customer, so what? So your interpretation could be that the customers with a certified anti-theft device are 40% less likely to file claim compared to those who doesn't have these anti-theft devices. So this feature is powerful indicator for low-risk customer segmentation. So what? sorry, now what, or your recommendations going could be. So this is just an example. I recommend that we introduce a new premium discount for policyholders who can prove that they have a certified anti-theft device installed. So this will attract and retain low risk customers, directly improving overall loss rate and so on. So having this understanding is very crucial. So is it clear, guys? Maybe before I move on, and I think I have taken a lot of time on this one. I just wanted you guys to have a clearer understanding. So can we move on? Can we continue? Can I see some thumbs up if everything is clear? So I have one. Yes, you know.
እንትን ፒ ላይ ማለት ነው።
ያ
ይሰማል።
yes ይሰማል።
ኦኬ እሺ። ፒ ላይ እንዴት ነው ፒን የምናገኘው ነው? ጀስት ከዛ በኋላ የመጀመሪያው ቴስት ላይ
ያ ኦኬ አይ ቀጥል። አይ ፒ ቫልዩ እንዴት እንደምናገኝ እናየዋለን፣ ግን እዚህ ጋር ጥያቄን ጠይቀኝ።
ያ ዜን እንዴት ሃው ኢንተርፕሬት እንደምናደርገው ነው። ጀስት መጀመሪያው አኖቫ ቴስት ላይ አሁን ከምናየው ላይ ሌዛን 0.01 አልንና ቻይ ስኩዌር ቴስት ላይ ደግሞ
ሪጀክት አደረገ።
ያ ሶ ወደ
0.05 ነው እንትናችን። yes so 0.05 is like ከዚህ በታችና ከዚህ በላይ ሲሆን ነው like I think we have seen p value ላይ በምናይበት sorry I think okay maybe I have lost the slides but p value ከ0.05 በታችና ከ0.05 በላይ ሲሆን ነው or ደግሞ 0.05 አካባቢ ሲሆን we will just have a different definition like accept እናድርገው ወይ ደግሞ reject እንኳን የሚለው ጥሩ ኤግዛምፕል አይደለም። ሪጀክት ከሚለው በላይ I think a better example or statement fail to reject the null hypothesis. Yes, so fail to reject the null hypothesis ማለት ይቻላል። So if the p value is less than 0.05 standard, so beyond a reasonable doubt እንደማለት ነው።
ስለዚህ አሁን ፒ ከ0.05 ከበለጠ we are going to say we are failed to reject.
Yeah. Yeah. So I think it's going to be very clear in the example. So እነዚህኞቹ ሲናሪዮ ስለሆኑ maybe እንደዚህ አይነት ኮንፊውዥኖች ነው ያመጡት። I think እንደውም why don't we ጎን ለጎን እያየን አንሄድም? Because I think the example is very related to let me just bring this one. ይታያል guys sorry just ይታያል አሁን slowly to yeah. No, okay. So let's have this so I think with example, I think it's good to go with the example. This one, yeah. So what I've done is just to have some. So it's basically very similar data with what you have. So what I have changed here is just I just used random. Okay, so just to have some, so just to motivate you to do it, I've just used some random data set. So here we have so we have the policy ID. So it's just a number. The satisfaction score, we have random between 0 and 10. The claim amount is just going to be the number of claims. So for the satisfaction score, I have chosen to go with the normally distributed data just to show, okay. And for the right claim amount, I have chosen to go with a right skewed data set. And for the support call last year is just a poisonous. This is just to show you what we have talked, just to show you in example. So we have the provenance, which is 4 provenances we have, and for the gender we have male and female. It has anti-devices, we have true and false. So this is just an example of the data set. So we have 2000 data points, and we have 7 elements. So we have the policy ID, satisfaction score, the claim amount, support. So the satisfaction score is a whole number, the claim amount, the support call last year's, provenances, which is just an object or categorical, and the gender is also categorical, and has anti-theft devices, just Boolean. So let's start with just taking it. So for the ANOVA claim, we will just make the amount of. So this just trying to. This just what do I say? Just correcting the data, I would say, just for the use of example. But for you guys, this is not going to be necessary. Okay, so you don't have to change the data, but I wanted to show the different cases that would happen. So this is just what I'm just doing. Okay, so don't worry about the first 2 lines, the first 2 cells of the code. So here we have the provenances. We have so average claim of, across the provenances. So you can see that I have made this provenance a bit higher, and we have the rest of the provenances here. And for the gender, it's just slightly, for the male is higher, but it's more or less similar. And for the anti-theft, you have this number. So claim rates, okay, so this rate, claim rate by anti-theft devices. So if it has an anti-theft device and the rate of claims. So the ones that doesn't have anti-theft devices has a higher claim, and for those who have, it's a lower claim. So so what we have seen earlier is just a way for me to prepare the data, because I'm not using real data. I'm just creating it. So it's just random data. So that's why I'm doing this. So if I work with the real data, it's like I've seen that it's just going to be a copy and paste. But yeah, it's just a way to avoid it. But I might remove them if it is confusing. Okay. So let's see the distribution of the data. So it makes sense, right? Like what I just talked. Nice. Does it make sense? Okay. So for the rest of you, doesn't make sense. Okay. Yeah. So let's start with the data. So let's see the distribution of the customer satisfaction score. So if you remember, while we were taking a look at the distributions, the statistical distributions, and when we were talking about the normal distribution, one of the examples that we have seen was that normally we would expect that the customer satisfaction score would be normally distributed. Actually, it's not fully normally distributed. As you can see, it's more or less skewed to the left. But yeah, normally the customer satisfaction score is a normal distribution. So here it would be symmetrical and bell-shaped. So for the rightly skewed, example, we can see the total claims. So a lot of people are on this on lower. So when we talked about the skewed, I think for the earlier example, we can see this graph. So for this graph, you can see a lot of people, the higher frequency people have lower claims, lower than $20,000 or 20,000 per. This tells us a lot of people are not like there are lower claim amounts for many of the people. So you may see that when you go to the insurance. So this is expected, right? Just to inform you that this is expected. So when you work in an insurance company, the claims that you see, many of them could be a small dent in the car. It could be with the mirror. It could be with the tires, like small claims. Of course, when we say small, it might not be very small, but compared to the others, it may be very small. So this type of claims are what a lot of people take take money for. But there are some cases, for instance, if the car is stolen, maybe, I don't know if we support that, but if the car is stolen, or if your house burned down, or if there's a riot and your car was destroyed in the process, like things like this could happen, but it's very low chance. So this is the right skewed example, a proper right skewed example. And for the poisonous, it's just the number of support calls followed by the poisonous distribution. So the number of calls and the number of policy holders. So the number of calls they make, you can see that it's also rightly skewed. Yeah, okay, so let's go to the hypothesis testing. So we will also see the three tests. So for the independent t-test, we will see what you have talked, which is if we will see that if there is a difference between the male and the female, and if there is a difference between the genders in their average claim. So if there is a difference in average claim between the genders. So our null hypothesis normally would be that there is no difference between the male and the females, and for the alternative, which is the alternative hypothesis, is going to be the male claim amount is different from the female. The mean or the average claim is different for the male and the female. So for this one, we use the t-test int, which is just is just method in the stats package. So here it will, so this test is going to automatically give us the t-stat and the p-value value. So we will just give it, so the male claims is going to be the total amount claim for the male, so where gender is equal to male, and we will just take the claim amount, and the female claims is just the data point where the claim amount where the gender is female. So we have two claims, so we just want to have the t-test independent, like the independent test here. So the result that we have found, so if the p-value is less than 5, we can reject the null hypothesis, saying that the difference in the claim amount is statistically insignificant. And if it is higher, we can fail to reject the null hypothesis. So it's not reject, like it's not accept, but fail to reject. Okay, so like the wording is, I think, while I was reading, I have seen that it's very different to accept and to fail to reject. It's a very different thing. So yeah, we should be careful with that one as well. So, and then we will see the mean, like the average between the two and their difference, and we will see if it is, it's appropriate. Okay. Yeah. So let's see. So here we have, so the result that we have found is 0.7835 for the t-statistics, but the p-value is less than is greater than, yes. Is that a question? Yes, Nabil.
I was just going to say, for people who are like not native speakers of English, the difference between accept and fail to reject, it seems small, but it's very meaningful. So accept meaning, when you say you accept something, it means you're actually actively, you know, giving it affirmative. But then when you say you fail to reject something, what you're actually saying is, I'm not actually giving this affirmative. I just say that it's not possible for me to give it the negative. So it's a small semantic difference with huge consequences in terms, if you're talking about being statistically rigorous. I just wanted to say that one point.
Yeah. Like during my research as well, I was surprised to find that it has like a very big difference. So like I just wanted to point it out, and thank you, Nabil, for the confirmation. Yeah. So like use the term fail to reject rather than accept. Okay. Okay. So here, like for the value, you can see that it's actually very big than 0.05. So you fail to reject the null hypothesis. So this would mean that there is a difference, the difference between the female and the total claims between the female and the male is not significant, statistically significant. And for to just what will I to just clarify on that, or to just like build up on that. So if you see the claim between the male claim is for like the average male claim is 4,613.88, and the female claim is 4,453. The difference is only 160. So this is very low, the difference. So you would see that it makes sense that you fail to reject the null hypothesis. So failing to reject the null hypothesis, like if it is the p-value is very greater than 0.05, you may go with failing to reject the null hypothesis, or like yeah, I was going to say accept, but fail to reject the null hypothesis. Yeah. So is that clear? Maybe I just wanted. I think the person who asked earlier, I think I forgot your name. Yes, yeah, okay. So let's go to the next example. I think let's go with the ANOVA, which is just an extension of the t-test. So here we will see that if there is a difference in average claim across the provenances, so we have four provenances. From the four, I just chose 3 to go with. So we have the Guteng, I think, WC and KZN provenances. So I just took their claims here, and I just used one way to do so the F-stat to just the ANOVA test, and I have these claims. So I just provided it, and we go back. It will return with the stats results and the p-value. So taking a look at the p-value, we can see that the F-stat, we have a strong F-stat result, and the p-value is actually very, very low, which is lower than 0.05. So in this case, we will accept, we will reject the null hypothesis, so that what we would think, or we would like, of course, there is going to be further analysis, but we can assume that there is a significant difference in claim amount between these provenances. So let's see if that's true. So taking a look at it here, so we can see that the Guteng has a very high average value, plus the count is very high, plus the standard deviation is very high. So we can see that the average claim taken by the Guteng provenance is very high, and the KZN and actually the Western Cape are very close. If you even see the count and the standard deviation between them is very close. And we can see that there are actually, like, if you compare only these two, you would actually see that there would not be any like this big difference. So you would actually fail to reject the null hypothesis, but for the good hang, it's very high and it's very significant. So that's why you will reject the null hypothesis. Okay, so this is just to prove or to help you understand why this result happened. Okay, and for the last one, for the chi-square test, we can see the association between the anti-theft device and yeah, is that a question or okay, I think it's a question. Hypothesis prompt. Abraham, I don't understand the question, but if you want to see it here, are you talking about this prompt or what is the prompt? Okay. Yes, yeah, you know.
The results that you show us, epistatics and alpha level, what tell us those numbers?
So alpha level is just 0.05, which is just, so you, like, if it is lower than 0.05 and if it is greater than 0.05, so that's just like for the p-value what you compare it against. So that's just there to show you that, like, I mean, like the p-value normal, not like, okay. Yes, Nabil?
I was going to ask a different question, but is the alpha level is is different than the p-value from what I understand. I might be wrong. For me, I thought the alpha level is the amount, is the percentage that you will be making a type 1 error. So the type 1 error, what that means is just rejecting a true null hypothesis.
Yeah, so that's the p-value, like if no, the p-value is, yeah.
So
okay, continue.
I was gonna ask, right? So is the p-value necessarily the alpha, or is it, or no. Can the p-value can also be talking about rejecting the type 2? The p-value can also have implications for the, what's the word for it, for the type 2 errors as well. So the two are different, right? There's p-value is one thing, and then you have the alpha, which is another thing.
Yes, but for this case, I think I think I have to change the wording here, but for the alpha value, I'm just using it as a p-value, like just using it as an information to just communicate as like what I would accept as my error and I would not accept as my error. I think
I understand. Other thing I wanted to ask was, when you program from a engineering standpoint, is there any significant difference for using if-else or using try-except? Is there any real difference for performance, or is the one preferable to the other, or are they pretty much the same?
I don't, like, currently I don't see.
So right now, when you for your error handling, you have if p-value, and then you have the else. But you could also do the exact.
If it is equal to 0.05, you mean?
No. What I mean is, so not talking about like the actual statistics here, but in terms of the actual programming, if you, instead of using if-else to do the error handling, is there any significant difference between using try-except?
No, of course, it is very different. But for here, it's not for error handling. For error handling, you should work is try-except. For this, I'm just checking the condition. If the condition meets, I will just print out these values. But if the condition fails to meet, I will just print out a second value. But for try else, it's going to try performing that, and if it fails, it will just go to the else block.
Yeah, I know.
Yeah, so it's very different.
Yeah, so I'm saying, but for error handling, you should be using try else. The question came up to mind, so I thought I would ask it while I was here.
Of course. For error handling, you should use try else, try except, but this is not for error handling. I'm not trying to, I'm not assuming that there is going to be any error. Yeah.
Exactly. You're just doing conditional statements, simple conditional statements.
Yeah.
Okay, thank you for answering.
This happens to that. Okay. Okay, I think there was someone else who had their hands up. Yes, Nathaniel Mami, the t-test is used to compare two categorical groups with a numerical value, and ANOVA is used to compare 3 and more groups with a numerical value, categorical groups with a numerical value. So here, I think you have seen Nathaniel. So here it was just for female and male, and here we have actually 3 provenances. So yeah, alpha value is a threshold. Yeah, I think I was looking for this word. I didn't have it on it. So ANOVA and t-test, what's the main difference? As I see, if of course, if the p-value is less than 0.05, and if it is greater than, and failing to accept the p-value and rejecting the p-value, doesn't depend on the test. It just depends on the p-value. So the test is just there to give us the p-value, but what we do is the interpretation doesn't differ. Johannes, is that clear? Johannes Alam. Okay, I think it was answered actually by for conventional cutoff present 5% chance of observing the result is. So, I mean, yeah, if the conventional cutoff point that represents a 5% chance of observing the result, if the p-value hypothesis is true. Sir Abraham. So, when you Surah, okay. I think it's answered by Abraham. I'm trying to understand your question and come up with an answer. It's a conventional, or is it? Or it's a statement. It's not a question, right, Abraham? Abraham, yeah, okay, yeah. Yeah, in that case, you are true. Because I was trying, I was thinking it was a question, and I was trying to, yeah. So you are exactly correct. So let's go to the last one. So we're trying to see if there is a relationship between anti-theft device that's installed in the car and having a claim. So they are both categorical. So the null hypothesis will be there is no association between them, and of course the alternative is going to be that there is an association between the two variables. So the first thing that we're going to do is cross table. So we will have a contingency table. So we will create a cross table. So just use the pandas from the pandas module. Just use the function cross tab. So you have both categories: has anti-theft device, which is a true or false, and has had a claim, which is also true and false. And of course, you can see the contingency table here. So for has a claim and for has anti-theft device, we have true and false. For both false, we have 970, and true, we have yeah. So I think this is not. I think I should change this one, because the first one is for the claim and the second one is for the contingency. So this is just a cross table. So I think this one, I would shorten this one. So the cross table is going to like have, so false, false. You can see this as, I think, correlation table. I think you have done the correlation table. You have experience with this, so you can see it as that one. So for both true, you have 68, and for true for has a claim, and false for has anti-device, you have 233, and for both false don't have anti-device, and yeah. So for this one, we use a try-to contingency method from stats, and here as well you can see that the p-value is 0, and the chi-squared statistics is 43. So you can see that you can reject the hypothesis that says that there is no significant association between the two, and you can like assume that there is a significant association between having an anti-theft device and having a claim is actually related. So that means having anti-theft device and having a claim does have a strong association. So you can actually see from the frequency, you can see that having claim and having anti-theft device is very high than both having true. But yeah, true and false and true false. Yeah. So you can actually reject the hypothesis, but I will actually think I would add more details to this one, but yeah. So is it clear, guys, before we move on? I think we haven't even finished the slides. I think I just remembered. So is it clear? But before, is it clear, guys? It's really clear. Okay, good. Thank you for the confirmation, but for the interest of time, let me try to move it a bit faster. Okay, let me share my slides and let's continue from it. So I think it's just a couple of slides. Okay, can you see the slides now, guys? Is it visible? Okay. Okay, so let's talk about common faults that we need to avoid while doing or while coming up with analysis or our insights. So translating results require a careful thought. So two of the very common pitfalls that you need to avoid are like these are like we see them everywhere actually. So confusing statistical and business significance. So for instance, a result can be like statistically significant, but have a tiny effect. For example, having one difference in average claim. But like you can see that this is happening a lot of time. So there is a difference, but having this much claim, the difference could not be very significant to the business. So the tips always ask, is the difference large enough to matter to the business? Focus your energy in finding on what focus on your energy in finding on both that matters statistically and have a meaningful impact. And the second one, which is actually my favorite thing, which is cohesion is not correlation is not cohesion. So what this means is just because it has a correlation doesn't mean it's the cause, right? So your analysis might show that the customer who own red cars have a higher rate claim. So the correlation may say that this is true, but like you should not conclude that the color of the car, which is for this one red, could cause risky driving. So just because you can see that there is a correlation between them doesn't mean it's you can conclude that it's a cause. So if people, like for instance in Addis, I think a lot of cars are silver, so having this mindset would really affect you. Like if a lot of cars are silver and they are taking a lot of claims, and if a car with the color red comes in, like if you assume that it's not going to have issues, or like if you conclude that they are not risky, it's going to cost you. So acknowledging that there may be a hidden variable, perhaps people who prefer the the color red car also tend to prefer sports car. So for instance, if you take a look at Ferrari cars, a lot of sports cars are red, so which is inherently risky. So you might the insight might should be we have found correlation. Our next step should be investigate the potential cause of before making any decisions. But just depending on the correlation and coming up with I think yeah, a decision is going to be very risky. So for the last one, let's just summarizing and your analytical starting point. So start with distributions, as we have said, like what we have seen from the flow of the slides. Actually, plot your key variables, understand their shape, center, and spread. Are they skewed or not? So this is your first insight into the data. And formulate your hypothesis depending on like what you have seen. Turn a business equation into a testable hypothesis based on the variables in your data, of course. And choosing the right test that you're going to be performing it with is also crucial. So comparing two variables, two averages, it could be the t-test, and if you are comparing three variables, average, you can use the ANOVA. And if you are comparing two categorical variables, you could see the chi-square test. And of course, the last one is translating your results. So do not just report the p-value, explain what it means for the business and your recommendation to the next step. So this is how you create value. So I hope this is very clear, because like I have tried. Yeah. Now I hope this is clear, because this is very crucial for your analysis and moving forward. So please do take note of it, and always remember the three questions: what, so what, and now what. So that I believe it's going. Maybe I will change the wordings if they're a bit hard, but yeah, when you do analysis, the one of the issues that I see is people do good analysis, but interpreting it and communicating it is a very different pain point. So yeah, please just try to follow this framework and perform the analysis, okay? And write the report. Yes, Nabil.
I was going to say, is that what you said? What really helps you is going from one shoe to the other. As an analyst, your goal is to figure out what the patterns are, but then you have to completely shift the business mindset. And then you have to say, and then when you're thinking about the actual interpretation, you have to think, what does it actually mean for the business? And then what are the implications, right? Like you're saying earlier, even if you have like a 0.000001 like p-value, but if like the difference is insignificant for the bit from a business context, then it really doesn't matter, even if there is a difference. But sometimes the p-value might be a bit higher, it might be 0.06, but it might be a much bigger issue you're looking at. So you have to kind of have both hats as you're going back and forth, and that really helps me when I do my work.
Yeah, couldn't have said it better. So yeah, like having, of course, like I know that for the training it might be a bit harder, like because we are jumping from industry to industry, like from scenarios to scenarios. But having, but of course, we have AI on our side, so having that business interpretation is very crucial when you do your analysis, because it could be like the decisive force between having like yeah, it's very important. Let me just start with that one. But yeah, please just try to follow a framework. So I think I should end with that one. Yes.
Hey, can you hear me?
Yes, we can.
Yeah, my question is, choosing the right testing method is difficult. So, is there any specific key parameters to choose the right testing method? You can tell us. Actually, you have mentioned like the kind of variables, like if they are two categorical variables, we are going to use chi-square method, chi-square testing. But and also, like, another question: how can we know a variable is categorical or not?
Okay. So yeah, so that's a very interesting question. Of course, if we are talking about like the null hypothesis, the hypothesis testing that we have talked about here, I think I have mentioned some of the key things that you can see. And one of, like, I think the last question, if I understand you correctly, like, how do we say it's a categorical
Yes.
and if it is not? So of course, like, that's really is like just see the type of the data, like just write d type and or just say info on the data frame, and it will show you the type of the data each column has. So if it is object or Boolean value and so on, you can see that it's object, like categorical value. Of course, like an interesting question could be, what if the number of categories is very high? So for now, what we have seen is just 3 or 4 categories, but what if it has hundreds of categories? So that could be, of course, you would use the same, like a similar tool for this one. Of course, ANOVA is going to be the one for testing your hypothesis, but just checking the type of the data and the type of the data type of the column by using, you can use info, like BF, like data frame.info. You can see the type of the data. If I have understood your question correctly, that's how you can identify if it is categorical or numerical. And for choosing it, you can just see, like, of course, you have to start with the question. So you have the question and you want to answer the question. So depending on your question and your data, you can choose the type of the test that, like, from the information that you have. So if it is categorical, if it is numerical, and so on and so on. So it depends on the question that you are trying to answer. So I cannot, like, I'm struggling to give you like a direct answer, because it depends. It's very depending on the situation that, or the question that you are trying to answer. So it's not like, it doesn't have a clear one answer for how to choose the right test method and so on and so on, because it might differ with your situation. So try to understand the data, try to understand, formulate the question or the hypothesis, and then if you do these two things, it's very easy to choose the type of the test that you can go with.
Yeah, thank you.
Nabil?
I was just going to ask, for lots of categorical not categorical, I would say, variables, the best way to actually analyze them, would it be to consolidate, or is it best to encode it for statistical analysis? I know encoding is usually used more like for like machine learning algorithms, but what's the best way to deal with if you have like a lot of different categorical variables?
So are you talking about the hypothesis testing? If you are talking about the hypothesis testing, like
Yes, to kind of consolidate it, because it can be difficult when you're dealing with many different, with a huge
of
quantity
course
of
it's
categorical.
like when I was trying to explain to Al, I was that was what's on my mind, because why if like we have a lot, like 100 or 200 categories, what would be the best way
Exactly.
to do that? So that's a good question. But the second option that you had, like I forgot it. What was it?
I was saying that I was thinking one thing that you normally would do in like data
Contact.
analysis is you just consolidate categories. So let's say you have like, I don't know, let's say you have 100 different car types. You just gotta
Yeah,
group
yeah,
them in. You just gotta group them
yeah.
into.
I understand that one. Like the second option that you had,
I was gonna say
like
encoding, right?
encode them,
Like
but
encoding them.
encoding them would be turning them into numerical.
Exactly. So you turn them into numerical variables and then somehow try to do a
And then
numerical analysis
that's
afterwards.
yeah, that's another way to do them, but I wouldn't advise them advise to go with the encoding. But the first option, grouping them into groups and treating them as such, is very, like, of course, one interesting thing to do would be, of course, like I'm just like brainstorming, like I didn't prepare for this one, just for
Mm-hmm.
the record, but like grouping them and seeing the group that outperforms, and like doing it like and doing the analysis for that group, like the categories of that group, and doing that repeatedly to just get the result that you want, would be, I think, a way also. But I would definitely do some research on this one, because like as I was explaining to Carl, like that was also on my mind. So yeah, maybe if you have encountered has something like this, and if you have found a solution, you can share. Nabil.
I will.
But
I will if I find anything. It's just interesting
yeah,
question.
yeah, it is very I also noticed it while I was trying to explain. But yeah, okay. Yeah. So is everything clear, guys? I think we are way over time. Yes, Nabil.
I was just trying
Oh,
to do a thumbs up. Sorry.
oh, okay, okay, good. So yeah, if everything's clear, thank you guys so much. Thank you, Nabil, for your participation, and everyone, Gal, and everyone that's writing for your participation. So this is very good for both of our sides. So like, let's try to keep this energy. Okay. Thank you so much, and see you guys in 30 minutes. We have gone over time, so sorry for that one. And I will share the slides in the notebook on the drive. So make sure to keep an eye on it. Okay. Thank you guys. Bye. Have a great day. See you guys